Hi there. This is part two of the video on how to do integration by parts. Look for the first part right next to this one. If you haven't seen the first part and want to see the basic idea for integration by parts, check out that one. I'm going to go through more advanced problems in this second part video on integration by parts. So you're seeing where I left off on the previous video, and I'm just going to jump into the next example and go from there. All right, so the next example is kind of down here. It may be hard to see, so I'm going to zoom in a little bit. It's this one right here. Find the integral of x squared e to the x dx. All right, so we're going to be using integration by parts. And as I said in the previous video, we're going to aim for u being a function which gets simpler upon differentiation. If I choose u is equal to e to the x, the derivative is itself, so it doesn't really get simpler. Maybe that'll work, but definitely x squared might be a good one to try initially because it does get simpler. It just goes to 2x when I differentiate it. So that's kind of a tip on how to choose u and dv in these problems. So I'm going to choose u is equal to x squared. That means the remainder has to be dv, which is the e to the x dx part. I'm going to differentiate the u thing to get du dx, but I'll move the dx on the other side. So that's what my du is. And I'm going to integrate both sides to get v. And the antiderivative of e to the x is just e to the x plus c. I'll save the plus c for the end. All right, so now that I have my different components, I'm going to write out integration by parts, and we're going to see what happens here, see if it gets simpler. So integral of u dv is equal to uv minus integral of v du. Let's put in the components. So we need u and v. Make some space down there. So u is this x squared thing, and dv is this one right here. So we're just going to verify that we do have the right integral, x squared dv e to the x dx. And that does match the original problem up here. So yeah, we have the decomposition correctly. Here's the v, so I have to do u times v. So x squared times e to the x is u times v. And minus integral of v du. There's the v, there's the du. So e to the x times 2x dx. So let me just clean that up a little bit. I'm going to move the 2 on the outside. And so I get x squared e to the x minus 2 integral, and I'll put the x in front just because that's tradition in mathematics to put the x in front of the transcendental function. So that's my new integral. So the first thing I want to ask myself is, did it get simpler? So the original integral is up here, x squared e to the x dx, and the new integral is x e to the x dx. Now, x e to the x dx is not as simple as I would prefer, but the question is not preference, did it get simpler? And the answer is yes. Before I had an x squared and e dx, now I just have x and e dx. So my exponent on the x went down. So it's a simpler problem. So that means I'm on the right track. I may not know how to get the answer yet, but again, did it get simpler? Yes, it did. All right, so now I need to focus on integrating this x e to the x critter. And that to me looks like two things being multiplied. Once again, x times e to the x dx. So I'm going to use, yes, integration by parts. Again, integration parts doesn't exhaust itself when you use it once. It's just a formula. You can use it as many times or as few times as you prefer. I think integration by parts a second time will help us get this even simpler. All right, so let me keep track of everything so I don't lose things. I have the x squared e to the x dx is equal to this x squared e to the x minus 2. And I'm just going to put a big parenthesis here so I don't forget the minus 2. And this is the integral of e to the x dx. Okay, I was a little aggressive there with the parentheses. Okay, there we go. All right, so there's my integral thing, and I'm going to do my integration by parts. Oh, I didn't write it correctly. Someone's like, where'd the x go? Yeah, it's because I'm doing things too quickly, and I forgot my x e to the x e to the x dx. So if you spotted that, good job. And I spotted it, so good job to me. Okay, so we're going to do our u dv thing. U is going to be x. It does get simpler upon differentiation. dv will be the remainder stuff, which is all that. Just a little smidgen over here. Okay. And then I'm going to find du, which is just 1 times dx. And v is equal to e to the x plus some c. All right. So we have our original thing I'm just trying to keep track of. And then the integral of x e to the x dx is going to be another uv minus integral of v du, thing like that. All right, so what is my uv stuff this time? Well, the u and the v and all the stuff, the u and the dv are right here, and the du and the, I just have to fill stuff in, right? I just have to put stuff into the formula. So uv x e to the x minus integral of v du e to the x times 1 dx. Boom. So now, again, did the integral get simpler? This is the new one. This was the old one, or at least, the second one we got. And it's definitely easier. It has no x's in it all together. So again, this tells us we're going in the right direction. In fact, when you realize that the one doesn't matter, the integral of e to the x is easy. We've already done that a couple of times. The integral of e to the x is e to the x. So we know we've gotten to a point where we can just use our known formulas and get the answer. All right, so the original integral, our x squared e to the x dx thing, was this thing, x squared e to the x minus 2 times some stuff, based on our first use of integration by parts. And that's going to be x e to the x minus, now, this thing still needs to be done. So the antiderivative of e to the x times 1 dx is just e to the x, because the 1 doesn't matter. And I'm going to put the plus c over here just because it doesn't really matter where I put it. I'll just put it at the end. Okay, so now I just need to collect some like things. UV minus, I just double checking that I didn't miss anything because I missed that x before. I'm just hoping I didn't miss anything again. That's uv minus integral of v du. Looks like I did it right. Okay, so we get our final result. After I just clean this up a little bit, we get x squared e to the x. I get minus 2 times x e to the x. I get minus 2 times minus e to the x, which is plus 2 e to the x, and then I get my plus c at the end. And there you go. Some people are wondering, do I need to simplify this? There's no real things you can add together or combine together. You could factor an e to the x out if you wanted to. So some people might write this as e to the x, x squared minus 2x plus 2, since all three of these terms share a factor of e to the x. You can do that if you wish. You don't have to do it. I'll mark both answers as correct. The only simplifications I really need you to do, and we'll lose points if you don't, is combining things together, not necessarily factoring things out. Although that's a nice skill to have and it does help some problems, it's not necessarily a factor to get the correct answer. All right, I got a 2 or 3 more problems to show you, but that was an example of integration by parts where we had to do it twice. We did integration by parts. It definitely made it better, but not better enough. So we did another integration by parts, and it worked out to get the correct answer. All right, so let's go on. Zoom in a bit. So I have the integral of e to the square x dx. This doesn't appear to have 2 things, but we saw an example of that in the video part 1. You can think of this as like 1 dx. So you can think of like u is equal to e to the x, or excuse me, e to the squared x. And dv is equal to 1 dx. And I'm going to just make some more space. And then you can go ahead and do our integration by part stuff. To differentiate e to the squared x, you have to use the chain rule. So the chain rule of this would be e to the squared x times the derivative of squared x. And this is actually du dx. So if I make this less messy, I get something like du is equal to e to the square root of x. The derivative of square root of x, you can check this if you want. I don't go through all the steps because I want to focus on integration by parts, but this is x to the 1/2. So it's 1/2 x to the negative 1/2, which is the same thing as 1 over 2 root x. And then I brought the dx over there. move this over here a little bit. So our dv was 1 dx, and that makes our v equal to x. All right, so we're going to do the integral of u dv is equal to uv, these guys multiplied, times this. And you may notice already that this is not necessarily getting simpler. So my formula, u dv uv minus integral of v du. My u is e to the root x. My dv is 1 dx. My u is e to the root x. My v is x. And then the new integral, which is our big test of whether it got simpler, is v du. V is x. And du is e to the root x times 1 over 2 root x. And there's a dx. And if we compare, is this simpler than the thing we started with? And it really doesn't look like it. I mean, I know we could combine together the x and the root x, but we're still going to have a more complicated integral than we started with. So this probably isn't working. You can go for some more working. Maybe you can use substitution or something on this one. You could try some more, but it does not appear to be working because it did not get simpler. So that didn't appear to work. And I'm not sure what else we could do. I guess we could let u be 1, but its derivative is 0, so that doesn't seem to help us. So what do we do for a problem like this? For this problem, the way I designed it, the way I would try to explain what's going on is that we have all our other techniques of how to do integrals. And we learned u substitution. We actually probably learned it in a previous calculus class, but we had homework on it, and we've been doing it, and there's videos on it for this class. So u substitution is one of our techniques. And we should remember that we can still use whatever other techniques that we have learned previously, even though this is like technically the integration by parts video. Let's not forget that we know lots of math. All right, so we're going to go back to this problem. With the u substitution, I'm going to let u be something which is like, not easy to integrate. I'm actually going to use the letter w because the u and the dv are going to get confusing with the integration by parts. So I'm going to do like w substitution, if that's okay. It's just using a letter. So w is equal to square root of x. And then I need to find dw to be able to complete my substitution. So the derivative of this, remember this is x to the 1/2. So it's 1/2 x to the minus 1/2. Which, as I mentioned before, is the same thing as 1 over 2 root x, or 2x to the 1/2, if you like, using our negative exponent simplification. And then we'll move the dx over. And eventually we'll solve for dx. So in this case, dx is equal to 2x to the 1/2 dw. Okay. So now I'm about to put stuff in. So my square root of x goes in for, or my w goes in for square root of x over here. And my 2x to the 1/2 dw goes in for dx over here. Okay. So my pen is not happy again. We'll make it work. So e to the square root of x is e to the w. And dx is going to be 2 x to the 1/2 dw. I'm going to take the 2 outside because it's just a constant being multiplied. And I have e to the w times the square root of x, or x to the 1/2, whichever you prefer, times dw. And some of you are saying, well, this doesn't look like it worked. It looks like, we still have an x thing left over in there that we need to get rid of in order to be able to do this antidifferentiation. And you are correct. But if you remember the way substitution works, we still need to complete all of the conversion of x's into w's. I'm going to pause for 1 second. So how do we convert that square root of x? Well, we're the one who made up w in the first place. If you remember, we made up this fact that w is equal to square root of x. So we just put that in here. And this becomes 2 integral of e to the w. And square root of x is just w, dw. And this now looks like two things being multiplied. There's e to the w being multiplied by w. And we can actually simplify this now using integration by parts. So this is now where we're going to do the udv thing and simplify this, sort of originally simplified integral using w substitution. All right. Quick pause again. Okay, so let's finish this just by using our standard integration by parts. So I'm going to let u be a part that gets simpler upon differentiation. That's going to be the u part, or the w part, excuse me. And then dv will be the rest. And then I just do, in fact, we did this in the last problem. We did it with, x's instead of w's, but we've done this problem before. So we're going to get, well, to integrate e to the w dw, we just use our integration by parts formula. So we get uv, oops, I got to write these out. Du is equal to 1 dw, and v is equal to e to the w. And then we just fill in our stuff according to the formula. So we get uv minus the integral of v du. V is e to the w, and du is just dw. And you can see how it did get simpler. So, our goal is to make this simpler, and we did. So good job. And the integral of e to the w is e to the w. And I'll multiply by 2, add the plus c. And we're almost done. Some of you may be wondering what else we have to do. And others may realize that the thing we have to do is put it back in terms of the original variable. So the original variable was x's, and we have w's. But remember, we're the ones who invented w's. We had it right here, w squared of x. So I'm just going to put this back in terms of square root of x's. And then we get our answer. Sorry, my pen's a little slow, but I got it. I got it. Okay. So substitution and integration by parts. So if you have not already paused the video to give one a try, this might be a great opportunity for part F. It's another one where you're going to use a combination of substitution and integration by parts. And watching me do these is great, but at some point, maybe give yourself a chance to try, see if you can get a good substitution or decomposition for parts, and see how far you can get. Maybe you get to the end, or maybe you get stuck somewhere. And then when you watch the rest of the video, you can see how to get yourself unstuck. But please give this a go if you're willing. And then after you pause, come back and I will show you the solution. Okay, so hopefully you had a chance to try that. And I've written out the solution. So there are actually many ways of doing this. There are different use substitutions and different integration by parts that will give you the right answer. So one of the ones I chose here is one of the ones where I see there's a ln of some trig function that seems to be very, very complicated. So I'd like to simplify the most complicated parts when doing my u substitution, or in this case, w substitution. So I chose u to be cosine because it appears here and it appears here. Once again, if you chose a different version, it'll still come out with the same result at the end. I just chose this one as a demo. So I have w is equal to cosine x. I find dw dx and I solve for dx. So my dx thing and my W thing go in there. So this guy's W, this guy's W, and of course, this guy's dx. So that's what I get. I get the sine x didn't go anywhere. The cosine x turned into W, and ln cosine x is ln W, and dx is dw over negative sine x from this guy right here. And then I simplify things, and I get negative of W ln W dw. And I've actually done that integral in one of these previous problems on integration by parts. So you may have seen that before, but I did it again real quick. We let the part that gets simpler upon differentiation be the u. That ends up being the ln w part, because the derivative ln w is just 1 over w, much simpler than a natural log. And v is the w dw part, and its antiderivative is w squared over 2. And then I do my uv minus integral of v du. That's this guy here, that's uv. And this right here is the integral of v du. And when I simplified it, my new integral is definitely easier than my original integral, which was the w ln w dw part. Now I just have w. And so that integral of w is just w squared over 2, much, much easier to do. So we succeeded in getting it simpler by using integration by parts, which is really simplification by parts, right? So I get this thing, I distributed the negative sign, and combined like terms together, and I put back in terms of x from w, right? So w was cosine x. So I just put in where it says w, I just put in the cosines. So each time it has a w in there, I substituted back. So it's back in the original variable. And that is the answer to example F, which hopefully looks like what you did. Or if you didn't, maybe you can see what I did along the way that could help you finish your solution as well. I have one last problem to demonstrate. It's not a long problem, but I figured I'd show you because it has a particular twist to it that sometimes students don't see. So that's, of course, this example G. For this one, what I'm thinking here, you have the multiplication stuff that you're used to seeing. And we would like to have u be something which gets simpler. So u is equaling x would be a nice choice because the derivative of x is just 1. The problem is we get dv is equal to secant squared x dx. And for a lot of folks, they're like, well, I don't know how to anti-differentiate secant squared x. So remember, not only does the u thing have to get simpler upon differentiation, but the dv thing has to be something that we know how to anti-differentiate. Otherwise, we're making the problem harder than it really was originally. So many students will look at this and say, oh, well, I'm doing something wrong because the secant squared is not something I can anti-differentiate. So this is what I wanted to show you. And some of you are already saying, but wait, don't we know how to anti-differentiate? Yes, we do. Yes, we do. Please have your table of integrals somewhere nearby. It's hard to remember all of the integral formulas. And it turns out that secant squared is the antiderivative of secant squared is one of our typical formulas. For me, it is number 11 on this list. The integral of secant x squared is tangent x. And you may remember from derivatives that the derivative of tangent x is secant squared. So the antiderivative of secant squared is back to tangent x. So I did this example just to try to show folks that we're not going to remember all the antiderivative rules. And the goal is to be able to get things that are on our antiderivative list, right? These are our common integration formulas. And so our goal is to get something that looks like or is on the common integration formula list, and then we can integrate it. And that may not be matching up with your memory. So that was the reason why I put this example in here. But it turns out that the antiderivative of secant squared, in other words, v, is just tangent x. And as we said before, the derivative is just 1. Move the dx over here. And so I get this thing, the integral of the, u dv thing. That's this guy here. That's u dv is equal to u times v. So x is the u and v is the tangent x, minus the integral of v du, which is tangent x times 1 times dx. All right, so once again, the question is this simpler than the original guy? The original guy had an x and a secant squared. And the new guy just has a tangent, which on the looks of it looks simpler. So I think we're happy. But again, we have to know how to anti-differentiate tangent x or simplify it to something that we know how to anti-differentiate. And knowing means it's on our list of common integral formulas. So let's see if tangent x is on our list of common integral formulas. And it actually is one of our known integrals. The antiderivative of tangent x is just ln of secant x. So that's one of our known formulas. So we get x tangent x. Antiderivative of tangent is ln of secant. And let's remember our plus c. And that is the answer to example G. And it's also the answer to the last problem on my examples on integration by parts. All right, so hopefully parts 1, part 2 gave you a good idea of how to do integration by parts. Give it a try in the homework. Let me know if you have any questions. And I hope you have an enjoyable day. All right, see you soon, hopefully in Zoom or on the next video.